All right, what we want to do is take a look at the execution of some recursive functions, particularly paying attention to the difference in how a tail recursive versus a non-tail recursive method executes. So first we're going to look at factorial, which you may recall is not tail recursive because it waits to perform this multiplication here until after the factorial of n minus 1 has been calculated. You can't perform any calculation until you know both terms, and we don't know both terms until this returns a value from factorial of n minus 1 once it reaches the base case. On the other hand, my palindrome method down here is tail recursive because it's got two base cases, and base cases, so long as they just return a straightforward value, are always safe. They can't do a recursive call, and therefore they can't violate that tail recursion rule of not doing any work after the recursive call. The recursive case is down here. We see it calls to palindrome, and we'll notice that the parentheses for palindrome start and close, all in this line, nothing outside of them, nothing done after the recursive call is done. All of the work is done on the way down, meaning we chop this substring up as needed to get the first and last characters off of it after we've checked and confirmed that the character at 0 and the character at length minus 1 are equal to each other. If they were not equal, we would have fallen into the base case here and returned false. Therefore, we know they are equal, and we can call on downward for the next version. So we'll trace a little bit of each of those. First, I want to look at factorial. So we all know that if we call factorial with something like factorial of 3, it's going to do n times factorial of 2, because it does the n minus 1 in there. And then for that one, to calculate it, to be able to get factorial of 2, it's going to need to do n times factorial of 1, and our code was written such that the base case is factorial of 0. So to get factorial of 1, we're going to have to do 1 times factorial of 0, which it does know. So we can calculate this one as 1 and use it in place of that recursive call, essentially replacing it to where we know n was 1, and that's 1 times 1, so this one will return up the 1 from it. Here n was 2, and we now know that factorial of 1 is 1, so 2 times 1 allows us to return up a 2 from there. And then we now know that factorial here was 3, and that factorial of 2 was 2. So 3 times 2 allows us to return up 6 from that recursive line, which allows the final return value from the method to be that 6 that was given there at the end. So that works beautifully for factorial, but we notice that it does a little bit of work on the way down by decreasing the n in the factorial there, but most of its math is done on the way up after the recursive calls return. So this is why we can't use something like a loop to flatten this out the way that the compiler can do for tail recursive methods, because a loop has to be done with its work by the time it iterates to the last number. This one isn't done with its work by the time it gets down to the last number. It has to go back and perform it. This does allow us to use the stack in Java of these method calls. You see them all sort of stacked up. That's how Java stores them. We can use that stack to restore to the previous state where n was 2 or n was 3 or so on. So it's a very useful thing, but it means that we cannot flatten it back out and get that nice tail recursive behavior that we would want to be able to compile down to an iterative version of the method there. So factorial as it's written is not tail recursive. If we wanted it to be tail recursive, we could convert it in this particular case. Not all methods can be converted to tail recursion, but factorial can be. And this should perhaps know because we know that there are iterative solutions to factorial. So it will still need to take the integer n, but often when we want to get a result, we also need a variable for that result. So we can make factorial tail recursive, but we do have to change its signature a little bit. I'm going to call this one factorial TR for factorial tail recursive. It follows the same basic structure otherwise, though. If n is greater than 0, then we've got some work left to do. Let's go ahead and put those brackets in there just to be nice and clear. And otherwise, we can return. The difference is in what we return in our base case. If we have gotten all the way down to our final base case there, that means that we have called factorial. Now, the n will get decreased by 1 the same way we did before, so that work is done, and the other work must be done of multiplying the result times our n on the way down. So this multiplication can be done because we know the value of result currently, it was passed in as a parameter, and we know the value of n, it was also passed in as a parameter. I should be calling the factorial tail recursive. So now I have recursively called to this tail recursive 1, and we see it's not doing the work outside, it's doing the work inside with the parameters here. So by the time I get to my base case, I will have done n times, n times, n times for each of those values of n, and my job is just to return the result. So this one, we can see, would get to the bottom, return the result, and then just feed that into the return line here. So each of those would just be returning back the value that was found on the way down. The work was done on the way down the recursive calls there, so that it would generate that result value all the way through. Similarly, palindrome, we can see how it performs as a tail recursive method, because if we call with something like palindrome Bob, it's going to need to check the two outside ones, which it does on the way down in the recursive call here. They do match in this case, and so it would recursively call for palindrome of O, which is a single character, which puts us into this base case here, and in that length is less than or equal to 1, so we return true because a single character is always a palindrome. So we checked B and B on the way down and saw that they matched, and we were able to strip them off. Then we check that O is just a single character, which means from here we can return true. And that value is allowed to just be pushed back up because the only thing at this line is whatever value got inserted in place of that recursive call, so that this one also is just returning whatever was handed up to it, the true value, and it immediately has its answer. The same as our tail recursive factorial here. Let's step through just to get an idea of what it looks like to actually execute and sort of how the context changes in these. Now, you may recall I've mentioned that tail recursive methods can be compiled down to loops in Java. And so this method actually will have been compiled a little differently than the factorial one was, because it is tail recursive. So when we debug, we'll notice that right at the end, and I'll show you there. So we run the program, we end up at this line where we want to store as a result the return value of palindrome there. We will step into palindrome, and we'll see it's going to check the length. The length is greater than 1 for race car, so we'll keep going. We will see that it compares the two characters, R and R at the ends. Then it's going to do the substring here to take those two characters off and recursively call palindrome there. So when it recursively calls palindrome, it now has the A's on either end. It's more than one character. Those do match, so we come down to the recursive case again. and we call for the CEC that shows here. It will find it's long enough, find they match, and recursively call one more time. Now the length is 1, so we should end up down in this base case. It returns true back to the previous recursive call, and you can't see it here, the return value for it, but it is, so you can imagine it's replaced with true and would return back to all of those previous recursive calls. Now, because this was able to be compiled down to a loop in Java, it's actually not going to return us to that line over and over again. It will just return the value there. So it flattens out, again, those recursive calls in reality, but it steps us through it nicely otherwise to show us the recursion that's planned for it, even if that's not what it was compiled down to. So we come back out of here. Now result can be given a value. Result is set equal to true, we can see down here, and we've got our value returned from that there. So you can see that the tail recursive methods operate just a little bit differently than the other ones because they have nothing left to do once they've hit either of their base cases in the case of palindrome or the single base case in the case of my factorial tail recursive here.